that the human body is in essence a quantum system that emits and absorbs energy waves, the means by which everything communicates with everything else. We saw that our human faculties are manifestations of attributes common to all that exists. Intelligence, for instance, is essentially the ability to connect events matching their energy waves, and our intentions are our human way to follow quantum propensities, also common to all systems. So, how do we bring one of these copies into our reality? In quantum terminology, this is the collapse of the wave function. A wave function is a mathematical description of the quantum state of a system. Things exist in potential copies or probabilities, and we bring this probability into the real existence when we observe it. The act of observation collapses the wave function of what we observe. That is, it transforms the object from being a probability to being a real object that we can sense in. The issue of time has always been surrounded by mystery and controversy. At the center of the paradox have been questions such as when did time start and when will it end? More perplexing, what happens after it stops? The same dilemma has occurred with the concept of space. If space ends, what exists after that? Einstein discovered that time ticks differently depending on whether you are near a large object or if you're traveling at different speeds. It was noted, for example, that if you happen to be standing on a very massive body, such as a neutron star, time would pass a lot slower compared with time for another person floating in space. The notion of time is probably the most controversial and little understood of all quantum concepts. The main reason for its obscurity has been that reality is composed of discrete units called quanta, and a quanta is a fixed snapshot of reality, like a static photo where time is superfluous, rather than like scenes in a moving video. Where the science of quantum physics found an impasse to explain time, perhaps quantum philosophy may help by offering rational explanations. We can start by asking, what makes a unit of time? A possible proposition would be that a unit of time is to link one cause with one consequence. The advantage of this proposition is that it allows us to see time in motionless pictures. Consider looking at a photo of a landscape. We have no trouble perceiving that it would take less time to go from where the photo was taken to a nearby object than it would take to go to a distant location in the background. If we see the act of connecting a cause with its consequence as not only a unit of time but also as an intrinsic observation, then we move one step closer to understanding time. One unit of observation is one unit of time, and since an observation occurs at a quantum jump, one quantum jump is the most basic unit of time. The reason that we see a nearby object as closer to reach than a distant object is because there are less numbers of observations separating us, that is, less quantum jumps needed to get to it. Consider the analogy of seeing a photograph of a town. The distance between two neighboring buildings is a lot shorter than the distance between one of these buildings and the faraway mountains in the background. It takes longer to travel to the mountains simply because we need a much larger number of observations to reach them. We need to observe lots of other buildings, many roads, and a variety of environmental features, whereas the number of observations needed to reach the neighboring house is limited to only a few objects. Looking at the contents of this fixed picture, that gives us information about time, and in the same manner, looking at a fixed quantum snapshot, we get information about time between events. Considering time as number of observations has another advantage. It allows us to discriminate past events. Here, we are not connecting objects in a photo, but numbers of observations separating live events. The larger the number of observations needed to connect with a particular memory, the further back in time this event is perceived. So, time is the perception of events in a snapshot of reality that are separated by numbers of observations, Frederick wanted to clarify. In one template, I may see that what led to the achievement of a simple goal, for instance, cooking a quick meal, involved a sequence of a few steps, and that the achievement of a more complex goal, such as flying from one country to another, was accomplished through a much larger number of observations. Thus I perceive the former task as taking a short time, and the latter as taking much longer. That's right, the prophet answered, and because you cease to exist when making an observation, being recreated after the observation, you're always perceiving only what the observation has generated, a full history of events where some exhibit as quick events and others as slow events. You need to come to terms with the fact that time is embedded in a fixed snapshot, and find an explanation of why its motionless content give the impression of time. This is my explanation. Time, therefore, doesn't exist as such, because reality is composed of discrete and fixed, self-contained moments independent of each other. Each of these snapshots bring its own history of sequences of observations, giving us the impression of that particular past and future. The impression arises from perceiving connections between fixed events in the snapshot, that is, by the number of observations separating them. In actual fact, therefore, the perception of time is perception of distance. The more observations needed to connect with an event, the longer the distance and the longer the time that we perceive. When we see a photo of us as children, we know that a long time has passed because in the fixed snapshot of this reality, many observations have taken place since then. That is, the us now and the us then are separated by a much larger number of quantum jumps recorded in this snapshot than with us of yesterday. An observation occurs at every quantum jump, where time stops, starting again at the next one. This means that the number of observations is the number of quantum jumps required to achieve something, and this is registered in fixed form in the snapshot. The more quantum jumps required to achieve a particular objective, the longer we perceive this time. Making a meal requires a lot less quantum jumps than traveling overseas, and this time is thus perceived as a lot shorter. Throughout this series, I have been pressing the notion that human qualities are manifestations of attributes common to all that exists. So, how can we explain this essential time characteristic? The speculative answer is that all quantum systems are subject to follow sequences of events. Time is the way you perceive a mechanism that is common to all that exists. All systems, whether they fall into your idea of being alive or dead, biological or inorganic, possess the ability to sense sequences of events occurring one after another at different speeds. They do it in the same way as you do, by connecting with potential templates of reality and responding to the history of the constituents in them. A molecule of water, for example, can perceive sequential differences between when achieving a particular objective, let's say connecting with another molecule to be a part of a lake. It responds to the ordering of the constituents in the lake, just like you do when responding to the constituents of an event such as going to the cinema. Make no mistake, the only reason that you are aware of time is that you can sense the separation between observations and the ordering of events, expressed as a particular past, and it's the same for all organisms and structures. Everything is capable of sensing this ordering of events, which you call time, because it is done through energy waves. Time goes together with space as space-time. It makes rational sense to believe that both starts and finish at every quantum jump, then restarting from zero again. At every quantum jump, we enter a timeless and spaceless world of probabilities. If we put together the different concepts that I have been covering, we can see how they fit quite snugly with each other. A unit of time is linking one cause with its consequence. This is one act of observation, and it occurs at one quantum jump. The act of observation generates a template, a snapshot of reality, a complete and unique fixed snapshot containing its own past and future. Since the history of quantum jumps is recorded in the snapshot, we perceive it as a complete universe. Events that required a large number of quantum jumps are perceived as further in the past or as taking longer than other events. If one is persuaded by this reasoning, the next explanation needed is, why do we perceive an arrow of time? Time always flowing from past to future. A speculative explanation would be that this is the impression caused by attributing the property of being the cause to some events and the consequence to other events. The cause always comes first. In reality, though, both causes and effects are generated simultaneously and timelessly in the quantum sea of probabilities. The illusion of time occurs when we perceive this snapshot as a complete physical reality. As you can see, the impression of time is not created by perceiving one snapshot after another like in a movie, but it is embedded within the same snapshot. That's why different templates of reality bring different times, because they have different contextual arrangements, making past, present, and future particular to that snapshot. That's also why the perception of time appears and disappears at every quantum jump, zillions of times per second. When a snapshot of reality is produced after the observation, the impression of time is created again from zero. Each new template brings a new sequence of events separated by different numbers of observations and giving you a different history and different impression of time. These theoretical explanations about how to conceptualize time in a manner that goes well together with the existing quantum principles follow the tradition that time has a beginning and an end. Every 10 to the minus 37 of a second, time stops and the clock is set back to zero. What we perceive as time, however, is distance between objects and events separated by different numbers of observations. The next challenge is to answer very important questions. Does past, present, and future really exist? When you see something happening, it is because it has already occurred, so are we only seeing the past? Also, if time as such is an illusion, is it also an illusion to believe that past events create our present? Quantum science taught us that the past is generated by present events, not the other way around. The implications can be paramount, in particular considering the radical effect that this interpretation may have in modern psychology. We are virtually facing the possibility that if our thoughts are acts of observation that collapse their wave function, then thinking thoughts alter the past. Our memories may not be set on stone after all. I will try to answer these intriguing questions in part 2 of this segment on time. In this episode, I addressed the highly controversial and little understood notion of time. Noting that time passes differently depending on where you are and how fast you are traveling, I explained that since reality is composed of discrete units called quanta, time exists in static snapshots, and it is therefore better explained as distance between the components in the snapshots, rather than as time as such. I said that what we perceive as time is in reality the number of observations that took to link the components in the snapshot. A unit of time is then one observation, and it takes place at one quantum jump. Interpreting time in this fashion can explain why we perceive some tasks taking longer than others, and it allows us to discriminate past events. The perception of time is thus better understood as perception of distance. Longer distance between two events in the snapshot implies larger number of observations, and it gives us the impression of longer times. I explained that an observation occurs at every quantum jump, where time stops starting again at the next one. This means that the number of observations separating two events is the number of quantum jumps required to link them in the snapshot. Making a meal requires a lot less quantum jumps than traveling overseas, and it is therefore perceived as shorter. I mentioned that the perception of time occurs when we perceive sequential differences, and that this is probably an universal or an underlying quantum mechanism controlling all that exists. The impression that time flows is probably produced by the fact that we associate cause and effect. I said that the impression of time is not created by perceiving one snapshot after another like in a movie, but it is embedded within the same snapshot. That's why different snapshots bring different histories. In part 2 of this segment on time in the next episode, I will be addressing issues that may sound as science fiction, except that they are not. Quantum science taught us that if time as such is an illusion, it is also an illusion to believe that past events create our present. I will be offering philosophical explanations that it is the decisions that we make in the present that create the past, not the other way around.